Have you ever wondered how Spotify seems to know the exact song you want to hear? Or how Netflix can guess the next show you'll binge before you even know it yourself? Or maybe how meteorologists can predict the weather for next week with surprising accuracy, while also getting today's forecast wrong sometimes. And here's the kicker. How is it possible that the same kind of math can explain everything from shuffling cards to nuclear explosions to how Google became the world's #1 search engine?
Curious about how the world really works? Not the myths, not the shortcuts, the real science behind everything we see and experience. On this channel, we explore mind-bending physics, unravel the secrets of the universe, and uncover the hidden patterns that shape our reality. If that excites you, subscribe for weekly deep dives into science and discovery. Hit like and share with friends. Your curiosity drives our next adventure. Leave a comment and let us know what puzzles we should solve together.
Well, the answer lies in one of the strangest stories in the history of mathematics, a story that starts not with scientists in white lab coats, but with a feud in Russia more than 100 years ago. This feud wasn't about politics, though politics definitely fueled it. It wasn't about religion, though religion was at the center of it. It was about math. And this math was so strange, so unusual, that it changed how we think about randomness, prediction, and even the very idea of free will. But let's back up for a second, because in order to appreciate just how wild this gets, we need to start with something deceptively simple: a coin flip. Picture yourself flipping a coin 10 times. Sometimes you get 6 heads and 4 tails. Sometimes you'll get 7 tails and 3 heads. It's messy, it's uneven, and it definitely doesn't feel like that perfect 50-50 split we're always told coins should have. But here's the magic. The more times you flip, the closer you'll get to that even split. Do it 100 times, and maybe you'll land on 52 heads and 48 tails. Do it 1,000 times, and you'll end up right around 500 heads, 500 tails. This is known as the law of large numbers, one of the earliest big ideas in probability theory, first proven by Jacob Bernoulli way back in 1713. It basically says if you repeat an independent event enough times, the average result will eventually line up with what you expect. That's why casinos don't panic when someone wins big at roulette. They know that over thousands of spins, the math will always work in their favor. But notice that word, independent. Bernoulli's proof only works if each trial doesn't affect the others. Flipping a coin, rolling a die, drawing balls from a bag, these are independent. But life isn't always so simple. What if people's decisions aren't independent? What if my choice influences yours? What if the weather tomorrow depends on what the weather is today? That's where the feud begins. Because in early 20th century Russia, one mathematician, Pavel Nekrasov, looked at huge sets of social statistics like marriage rates, crime rates, and birth rates, and he noticed something remarkable. They seemed to follow the law of large numbers. Year after year, the numbers stabilized, as if human decisions were behaving just like coin flips. And Nekrasov thought he had discovered something profound, that this pattern proved people had free will. After all, if their choices followed the law of large numbers, then the choices must be independent. And if choices are independent, doesn't that mean they're free? Not everyone agreed. In fact, one mathematician in particular was furious. His name was Andrey Markov, and what he did next would not only humiliate Nekrasov, but also give us one of the most powerful mathematical tools ever invented, one that now sits at the heart of Google, Netflix, Spotify, and even modern artificial intelligence. And it all started because Markov decided to pick a fight. The feud that changed probability. Russia, 1905. The empire was in turmoil. Protests, strikes, and uprisings were spreading across the country as socialist groups demanded political reform or the Tsar's resignation. The nation split into two camps. On one side, the Tsarists, defending tradition and authority. On the other, the socialists, pushing for radical change. And believe it or not, this divide reached all the way into mathematics. On the Tsarist side stood Pavel Nekrasov, sometimes called the Tsar of Probability. Nekrasov was deeply religious, fiercely loyal to the empire, and he believed that mathematics could be used to justify free will and even the will of God himself. On the socialist side was his intellectual rival, Andrey Markov. Nicknamed Andrey the Furious, Markov was an atheist with zero patience for sloppy reasoning. To him, Nekrasov's attempts to connect mathematics with theology were not only wrong, but offensive. In his words, they were nothing less than an abuse of mathematics. The heart of their feud was the law of large numbers. Remember, this law says repeat an independent event enough times, like flipping a coin, and the average outcome will settle into the expected ratio. Nekrasov believes something bold. If you observe the law of large numbers in real data, you can infer that the underlying events must be independent. For example, when he looked at statistics from Belgium in the mid-1800s, he saw that about 29,000 marriages took place every year, year after year. The number stayed stable, just like coin flips balancing out in the long run. To Nekrasov, this was proof that each marriage was an independent decision, proof that people were exercising free will, proof that human choices were in some sense divine. But Markov thought this was nonsense. Why? Because Nekrasov was assuming the very thing he was trying to prove. Just because a data set looks stable doesn't mean the underlying events are independent. Stability doesn't automatically mean free will.
So Markov set out to demolish Nekrasov's claim once and for all. He needed an example where outcomes clearly depended on each other, but where the law of large numbers still held true. And he found the perfect candidate: language. Think about it. If you look at letters in a text, they're not independent. The chance of seeing a vowel or consonant depends heavily on the letter that came before. If you see a Q, the next letter is almost certainly a U. If you see TH, the odds are sky high that an E is coming next. So Markov grabbed one of Russia's greatest literary works, Eugen Onegin by Alexander Pushkin. He stripped away spaces and punctuation, leaving a string of 20,000 letters. Then he started counting. First, he calculated the overall ratio, about 43% vowels, 57% consonants. Nothing unusual there. But then he looked at pairs of letters. If the letters were independent, you'd expect vowel-vowel pairs to appear around 18% of the time, since 0.43 times 0.43 equaled 0.18. But when Markov actually counted, they showed up only 6% of the time, way less than expected. This proved the letters weren't independent. They were clearly dependent on what came before. Now came the genius part. Markov built a kind of prediction machine. He drew two circles, one for vowels, one for consonants. From each circle, he drew arrows to represent the probability of moving to the next type of letter. For example, if you're at a vowel, there's about 13% chance of another vowel, and an 87% chance of switching to a consonant. From a consonant, the odds are different again. What he had built was the first Markov chain, a system where the next outcome depends only on the current state, not the full history. Then he ran the numbers, and what he found was astonishing. Even though the letters were dependent, over the long run, the ratio still converged to the same 43% vowels and 57% consonants. The law of large numbers still worked. Markov had just proved Nekrasov wrong. You don't need independence to see the law of large numbers. You don't need free will. You don't need God. All you need is a chain of dependent events, a Markov chain. And with that, Markov had not only won the feud, he had created one of the most important mathematical ideas of the 20th century.
What he didn't realize was that his invention would one day be used to model the weather, understand diseases, build search engines, and even lay the foundation for artificial intelligence. But for now, Markov was just happy to humiliate Nekrasov. He even ended his paper with a cheeky line aimed directly at his rival. Thus, free will is not necessary to do probability. Mic drop. From poetry to the atomic bomb. Fast forward a few decades. It's 1945, the closing chapter of World War II. In the New Mexico desert, scientists detonated the world's first nuclear bomb. The explosion lit up the sky with a force equal to 25,000 tons of TNT. This was the result of the Manhattan Project, a 3-year effort that brought together some of the sharpest scientific minds alive: J.R. Robert Oppenheimer, John von Neumann, and a brilliant but lesser-known mathematician named Stanislaw Ulam. Now, nuclear bombs aren't just about chemistry, they're about probability. Here's the challenge. Take a lump of uranium-235 or plutonium-239. When a neutron hits the nucleus of one of these atoms, the nucleus splits apart, releasing energy, and crucially, more neutrons. Each of those neutrons can then hit another nucleus, triggering even more fissions, releasing even more neutrons. It's a chain reaction. And the key question is, on average, does each neutron trigger more than one additional fission? If the answer is yes, the reaction grows exponentially and you get an explosion. If the answer is no, the reaction fizzles out. This average number, the multiplication factor, usually called K, is everything. If K is less than 1, no bomb. If K equals 1, you get a self-sustaining reaction, good for nuclear power. If K is greater than 1, you've got the makings of a bomb. But here's the problem. Neutrons are unpredictable little beasts. They zip around at high speeds, bouncing off atoms, sometimes getting absorbed, sometimes escaping the core entirely, sometimes triggering fission. Their paths are chaotic, and the number of possible interactions is astronomical. How do you even begin to calculate K in such a messy system? For a while, even the best mathematicians were stuck. They could write down the equations, sure, but solving them exactly was hopeless. There were just too many possible outcomes. That's when Stanislaw Ulam had a surprising idea, and it all started with a deck of cards. See, after the war, Ulam fell seriously ill with encephalitis. During his long recovery, he passed the time by playing solitaire. Game after game, he wondered, what are the odds of winning a randomly shuffled deck of solitaire? Now, there are 52 FA possible arrangements of a deck. That's about 8 times 10 to the 67th. Far too many to calculate directly. But then Ulam thought, what if instead of calculating every possibility, I just play a bunch of games, record the outcomes, and use those to estimate the probability? It wouldn't give a perfect answer, but it would give a good enough approximation. That was the spark. If you can approximate solitaire by sampling outcomes, why not do the same for neutrons? When Ulam returned to work at Los Alamos, he shared the idea with John von Neumann. And von Neumann immediately saw the potential, but also spotted a problem. Solitaire games are independent. One shuffle has no effect on the next. But neutrons don't behave independently. Each neutron's fate depends on its current state, its speed, direction, and whether it's already scattered.
So you can't just pick random outcomes blindly. You need to model chains of dependent events. And that's when von Neumann realized this was exactly what Markov had invented decades earlier. A neutron's path through the core could be represented as a Markov chain. Here's how it worked in simplified form. Start with one neutron. From there, 3 things might happen. It scatters off an atom and keeps moving. It gets absorbed or leaves the system, end of the line.
It hits uranium-235, causing fission and releasing 2 or 3 more neutrons. Each of these outcomes has a probability attached, probabilities that depend on the neutron's current state. So you trace the neutron's path through the system, step by step, updating the chain as you go. Then you repeat the process hundreds, thousands, millions of times until the probabilities settle into a reliable estimate of k. This was revolutionary. For the first time, scientists could get usable answers for problems too complex to solve analytically. Ulam and von Neumann ran these simulations on the ENIAC, one of the first electronic computers, and they gave the method a name, the Monte Carlo method, after the famous casino in Monaco, because it relied on random sampling and chance. The Monte Carlo method turned out to be a game changer. It wasn't just about bombs. Soon, scientists were using it to design nuclear reactors, model particle physics, and study everything from fluid dynamics to finance. And at the heart of it all was the same idea Markov had invented decades earlier: dependent events linked in a chain. It's almost poetic when you think about it. Markov started with Pushkin's Eugene Onegin, counting letters in a poem. And decades later, his method was used to model the chain reactions that unleashed nuclear fire on the world. The strange math of Markov chains had gone from poetry to the atomic bomb. But that was only the beginning, because in the 1990s, the exact same math would decide which company won the race to organize the entire internet. From Pushkin's poetry to nuclear physics, and from card games to artificial intelligence, the journey of Markov chains shows us something profound. The same strange math can explain wildly different worlds. At its core, the idea is simple. The future doesn't depend on everything that came before. It only depends on where you are right now. The next letter, the next neutron, the next web page, it all unfolds step by step, with probabilities guiding the path. And that's the real magic. Out of randomness comes stability. Out of chaos comes prediction. Whether it's modeling the weather, recommending the next song you'll love, or even helping Google rank billions of web pages, Markov's discovery continues to shape our world in ways he could never have imagined. All because one mathematician, furious at sloppy reasoning, decided to prove a rival wrong. So the next time Spotify cues up the perfect track, or Netflix somehow knows your guilty pleasure show, remember that behind the scenes, a 19th century Russian feud is still playing out. The strange math that began with a poem has grown into one of the most powerful tools humanity has ever created. And it all started with a coin flip.